Hello everyone, I hope you all are doing well. So, in this session, I'm here with the basics of CAE and FEA. So, I'll be covering the basic interview questions of CAE domain related to FEA, CAE, CFD, stress engineer, as well as R&D engineer roles in future. Okay, so I'll be covering a set of parts like part 1, part 2, part 3, and so on. So, in the Part 1, I'll be covering a few things, and later on I'll add up all the required basic stuffs for the uh, CE interview questions as well as CE basics. Okay, let's get started with this. So when it comes to the interview, if you're going to deal with this CE interviews, so they will ask you about your industrial experience. So that is the key point to add up the attraction towards your profile. So try to recall all these steps which you have done during your past industrial experience. Okay, recall everything and try to gather more and more details and try to get into deep whatever the things you have done before. So that would give you the better impact during this interview questions. Okay, so add your industrial experience in a well-defined manner and execute it in a better manner. Okay, the plus point. When it comes to this FEA, so what exactly is the term FEA? So in short, finite element analysis is the method to solve the numerical equations dealing with the entire model, considering that one. So we're gonna just discretize it in the form of small elements. Okay, and once you convert that particular entire model into a simple mesh, you're going to apply the boundary conditions and solve for the results. Okay, so this is what exactly we're going to do there. So when it comes to technical terms, so it's a process where exactly we gonna just deal with the approximate numerical solution to the governing equations. Okay, to achieve this, what exactly we're going to do is, so we're going to convert these mathematical model to a set of algebraic equations, and we'll solve them to get the results. Okay, in short, in simple, we can say. Yeah, so here the same question again. So this particular method, that is finite element analysis, is popularly used to deal with the structural analysis, the dynamic analysis, vibration, heat transfer, fluid flow, CFD and all, and many for physics. Okay, even like the vehicle impact and the drop test analysis, even the pressure vessel analysis, even we can consider this submarine pressure hull testing and all. So in these all the domains we're going to use this finite element analysis. So when it comes to history of this FEA, so the paper, that is stiffness and deflection analysis of complex structures, which is published in 1956 by Turner and Claw, Martin and Toff, is generally considered to be the birth of finite element method. Okay, during 1956. So in the year 1960, the finite element term was coined by Ray Claw. Even during the same year, the program invented, that is an Naston, sorry, it was just Naston. Okay, and meanwhile other programs like the Ansys and Abaqus and so on. Well, so generally this finite element analysis is to replace the problem P, we can consider with a discretization, that is Pn. If we consider the solution of this particular Pn and Sn will tend towards the solution of the P and S. Okay, so it's a numerical method which will just separate the complex geometry into a mesh. Okay, so as I told, discretization. This mesh consists of elements that are connected by nodes. So each elements displacement can be solved using this particular equations, the partial differential equations and others, and finally you're gonna get the results. Yep, we will see about this partial differential equations and equation of motions now. So to solve this stiffness matrix, okay, the problem needs to be expressed in the form of the partial differential equation. So we already know that. So if you're new to the basics of CAE, so remember the partial differential equations will be used to solve these all the numerical models. Okay. So this particular equation involves with respect to the partial derivatives of the multivariable functions. So if you consider the basics, okay, so let's say if I consider the simple bar with the axial loading condition, okay, so which will just follow the Hooke's law under the elastic limit, okay. So if you want to just take that one into normal analysis method, we can start with the definition of the stress, strain and the Hooke's law. So once you consider the stress, the formula is the load divided by cross-sectional area, right? The strain, we define it as change in length to the length, like the original length, okay? So when it comes to Hooke's law, it is Young's modulus, which is equal to stress by strain. So where stress, which is equal to Young's modulus into strain. So again, this equation can be just again reconstructed. Could see the load, which is equal to area into stress, and that we can just add up the stress value. It is AE by strain. E is the Young's modulus. So once you again add into the derivatives, it is AE into du by dx. So it is change in length to the original length, u2 minus u1 divided by L we can consider if we consider the above particular scenario into account. So once you solve for delta x, the final derivative is d by dx of a into change in length to the original length plus force, which is equal to 0. So this is how we're gonna form the equations. So now what exactly this Young's modulus is? So very important term. So you could see there, I have given some example for you. If you take steel or example like the material properties like yield stress, which is equal to 300 megapascal, when it comes to strain, the value is given. So Young's modulus is stress by strain. So it is 15 into 2 is 30. So it is the value here. That is 200 gigapascal or 20 10 to 5 Pascal. Okay, 1 Newton meter square, which is equal to 1 Pascal. Okay, remember that. So this is how we're gonna just formulate these things. I hope it's clear. This is quite simple. Yep. So here when it comes to the equilibrium equation, the formula you could see here is the general equilibrium equation, which is equal to stiffness matrix into distance, which is equal to that is f of t. That is the static analysis formula. When it comes to the overall equilibrium equation, that is m is the mass matrix into acceleration plus damping matrix into velocity plus stiffness matrix into displacement, which is equal to p of t, that is applied load. So just at the right side corner you could see for the static analysis, as I said, it is stiffness matrix, it is displacement, which is equal to p. For buckling, the formula is the vibration, it is same thing. When it comes to the time based and frequency based dynamic analysis, the formula is the final one. Okay, so this equation you need to remember. So they might ask you during the interviews in the terms of basics also, you should remember this formula. Okay, for the static analysis, this mass and the damping will just be a constant, or we can consider it as 0. It will be converted into the static analysis. Okay, fine. To elaborate more about this stiffness matrix, in short, if I consider F is equal to K into U, that is global stiffness matrix into displacement, which is equal to nodal force, It is simply the stiffness matrix is used to relate the stress to known strains. Okay, you could see the explanation below. So in order to find the solution for the partial differential equations, the finite element method is used as the numerical method to find the solution. Okay, in the process, the stiffness matrix represents the linear equations. Okay, so these linear equations will be used to find the approximate results for the differential equations. Okay, in short, the stiffness matrix is the formula which will be converted in the form of linear equations to get the results for the differential equations. I hope it's clear. Fine. So now again, when it comes to the better explanation of this particular stiffness matrix in depth, we'll consider the same thing, that is, okay, element with the two node points, okay, in axial direction loading condition. So if I consider the matrix into account, the partial differential equation is F is equal to K into U, where K is the stiffness matrix, U is the vector displacements, F is the vector of forces. Okay, when it comes to a spring, okay, the behavior follows the Hooke's law that we already know. That's the basics. Okay, that is F is equal to K of X. So same thing when it comes to the static analysis, the same equation is followed. Okay, so we'll consider that a single element example. So assume that the nodes in the elements have the axial loading condition. Okay, so the formula is F1, which is equal to stiffness matrix is A into X modulus into U1 minus U2 divided by L. So same thing for F2. Okay, when you solve for the stiffness matrix, the formula is here, AE by L minus AE by L minus AE by L and AE by L. So once you put this one into the formula, above formula, this is what you want to get. So in short, the stiffness matrix is the simplification of the entire differential equations into the linear equations to provide you the results accordingly. I hope it's clear. If you take the same particular formula into account, if you solve for three nodal forms, so the formula is like this, where 2 AE by L term is the sum of the A by L term, since this particular second node is shared between the both the elements. Okay, this will be used for complex analysis as well, so it will keep on increasing. So we'll take the simple example. Okay, so here the same condition, two elemental model, so a three elemental model, sorry. So the first node is fixed, okay, at the corner, second node is in the middle, third node we're going to apply the load of 6900 Newton force. Okay, the equation will be written in the form of this. Okay, where F1 does not have a defined value, so that we need to find out right at that location. So the equation can be solved by using the following values. Like you could see, the area is 1 meter square. Young's modulus, here is the formula we already know, 69,000 megapascal. If you just solve for it, you will get the same thing. So L, which is equal to 1 meter. Okay, stress by strain we can add and we can find out the Young's modulus value. It is not that much difficult. So once you add these all the values inside the formula, you're going to get this formula, and if you solve this particular matrix, you'll get F1 is the reaction force at the fixed point. It is minus 6900. So basics it is, we already know that we'll get the same value. Displacement at the second node it is 0.1, and displacement at that third node it is 0.2 meter. If you solve the same thing using software, you're gonna get the same thing. So if you want to validate it, you can carry out the same particular problem into the software as well, and you can validate it. I hope you got the clear-cut idea about what exactly the stiffness matrix at the moment. Okay. Yep. Well, so we'll see a few of the questions again here. So how are we gonna solve the engineering problems regularly? So there are three methods. One is the analytical method, and the numerical method, the software, experimental method as well. So these are the three methods. So when it comes to numerical method, what are the different types? One is the FEM, that is finite element method, boundary element method second one, finite volume method, and the finite difference method. So when it comes to the finite element method, what exactly is happening there is, so this particular entire model will be consist of the nodes and elements, right? We know that. So the calculations are made for the nodes and the results will be interpolated for the elements. So this is what exactly we're gonna do with FEM. When it comes to the boundary element method, we're gonna just calculate the boundary node things and we'll just interpolate the results with the elements. Only boundary nodes will be taken into account here. Finite volume method, so this is used to solve the Navier-Stokes equations, okay, and applicable for CFD analysis. FDM is for the Taylor series. For advanced dynamic analysis we use it. Well, so as I explained this FEA terms we already know, so what exactly is going to happen. So when it comes to this shape function, what it is, we need to remember the shape function is going to take very important role in FEA. So what exactly it is? It is the backbone for the finite element method. It plays very crucial role for converting all the weak form equations into a set of computer solvable algebraic equations. So that we're gonna see later on. Now, how exactly this shape function will be formed? Okay, first thing is the differential equations, which is obtained by considering the physics, kinematics, and dynamics of the physical problems. So the weak form can be obtained using the different approaches like the weak principle or the 𝐂𝐀𝐄 residual method. Okay, these weak forms will be uh, added here, and once that is done, we're gonna solve it for the shape functions. Okay, this all the weak form equations will be solved in a discretized computational domain to get the shape functions. So what is this thinning of metals? So this particular process where the material thinning will happen due to the Poisson's ratio as well as increase in length. Okay, very important thing. So what and all the material properties we need to consider for the linear as well as non-linear analysis, right? So this is the very important questions which will be asked during the examinations or any of the interviews as well. Okay, we'll see here. The first thing is the static analysis. So if you consider it only for static analysis, we can consider the Young's modulus, okay, the Poisson's ratio, and the mass density. To calculate Young's modulus, we need the stress by strain value. Stress is the yield stress there. Yield strength we can consider, and we're gonna get the Young's modulus. Fine. So for linear dynamic analysis, what exactly this linear dynamic analysis? Which is frequency based. The models is make, okay, the frequency analysis as well. So here we're going to consider the same thing, the Young's modulus, Poisson's ratio, mass density. Non-linear contact analysis, it is also same. Okay, Poisson's ratio, mass density, and Young's modulus. When it comes to non-linear dynamic analysis, same thing. Okay, Young's modulus, Poisson's ratio, and the mass density. For non-linear material, we're going to add one more term, that is stress strain curve, along with the hardening rule. Very important thing. Okay, for fatigue analysis, Young's modulus, Poisson's ratio, mass density, including stress strain curve, that is fatigue life curve we can say. So what is the star mark here? Which is the mass density only required if you have the mass elements into the analysis, like which gonna add the acceleration due to gravity into account. Remember that in short. Fine. Yeah, so when it comes to this question, so using a different material will give you a different stress for a given strain. In short, the question is, if I use the different material, the stress results will be same or not. So this question has been asked multiple times. Even I had gone through this particular question multiple times. Okay, so we'll take a simple example here to just explain this. Okay, if you consider the beam column finite element case, so the Young's modulus, the Poisson's ratio, and the density will be taken to form the stiffness matrix. Okay, E by L, we have seen it, right? So same thing, the advanced formulas and all. So after you analyze this, so what exactly you do? So you're gonna form the strain matrix to derive the strains. Okay, and from your material properties, we'll get the stress results. Okay, so when you add the bending moment, axial stress, shear forces diagrams, so that will be developed in the structure, uh, given that the geometry is constant. Okay, so if you consider this condition, and the material, if you consider that should be under elastic limit, okay, so it will take the Hooke's law into account, that is stress which is equal to Young's modulus into strain. Okay, this relation will be taken into account. When this reason why when you have a column under the pure axial loading condition, so the same stress, that is, will get the same stress. So the strain will change if you change the Young's modulus. This you need to remember. The strain will remain constant for the same axial force in the cross-sectional area. If you account for the non-linearities, the whatever the Hooke's law you're going to consider, it is not applicable. So under the elastic limit for the static analysis, the stress will remain constant in short. Okay, I hope it's completely clear. So in more convenient way, so if you're going to consider the stress, it is independent of material for static analysis for the same cross-sectional area, length, and applied force. So if you consider steel, aluminum, brass, all the materials will get the same stress results, but displacement will vary. Okay, remember that much. So if you consider the plastic region, so what exactly happens there is the combination of tensile and shear force will take place. The material shrinkage will happen. So this Hooke's law will not be applicable there. So their stress results will start vary. Yep, so this is the explanation for this question. I hope it's clear. Yep, so here the discussions on true stress and true strain and what it does matter, what exactly it is. So this is very important thing, guys. So if you're going to deal with the engineering stress strain and the true stress strain, I'll just take you take you through your past. So if you're the mechanical engineer or the aeronautical engineer, so you have gone through this universal testing machine, right? So where we have conducted this tensile testing. So a simple rod will be taken into account. It will be stretched from one end will be fixed. We'll note down the displacement results along with the force which we have applied, and we'll convert that into the engineering stress, and we'll find out the true stress strain values as well by using these things. So that time, during that days, we didn't know why we are doing, so we simply did like idiots. Now when it comes to CAE domain, it is very important. We'll see exactly how we're gonna implement these things here. Okay, so traditional tensile testing machine we already know, right? So in the laboratories and all we have used it. So the procedure is to calculate the true stress strain results there. So to calculate this engineering stress and engineering strain, we have used the formula that is force divided by area for engineering stress. For engineering strain, it is change in length to the original length. Okay, these formulas. Okay, so at any point of during this test, so what exactly we have done is we simply converted the load versus displacement plot into the engineering stress strain curve, right? You could see the diagram there. So whatever the stress strain data we're gonna get, it is not obvious at first, right? So then with little considerations becomes apparent. So while engineering stress and strain, so inferred directly from force and displacement data, might be reasonable at the beginning of the loading. Okay, during the initial stages, the specimen is changing the shape as the load increases. We already see, right? So the Poisson's ratio will take place there due to the metal shrinkage. So meaning that the values that we have used in our calculation above, namely original length, we have taken, right, for the engineering stress strain, and even the cross-sectional area is the original only. So this becomes less valid or true. So the specimen is thinning due to the Poisson's ratio, right, due to this increase in length as well. Okay, meaning that the stress is actually higher in that region, and even the incremental strain is lower at that region. So these things we need to consider during this analysis. So to find out this engineering stress strain, we have to use the original cross-sectional area and the original length for consideration. So now how exactly we're gonna relate this engineering stress strain into the true stress strain? Let's see here. You could see under the assumption that volume of the material remains constant throughout the test, that we need to consider. If we take that one into account, so the volume is area into length. Okay, so if I consider the test after the test, okay, and before the test, it is same A0 L0, and which is equal to EI Li. So if we solve for the area for subscript instantaneous area, the formula will be A0 L0 divided by Li. Just remember this. So if you want to find out the true stress strain force over the instantaneous area, that the engineering strain is change in length over the original length, we can just manipulate this equation to find out the true stress strain. So to deal with this, true strain, which is equal to force for instantaneous area. Okay, when I consider this instantaneous area, the formula you can see, just grab it and add it here. Well, for the engineering strain, formula is change in length to the original length. It is Li minus L0 divided by L0. So if you just short it off, Li divided by L0 minus 1. So if you just replace this one that side, engineering strain plus 1, which is equal to the same Li minus L0 minus 1, right? So you can write the equation for true stress, which is equal to force per unit area, that is engineering stress inside bracket engineering strain plus 1 for the true stress. Quite simple, right? True stress, which is equal to engineering stress plus engineering strain plus 1, sorry, inside bracket multiply. So when it comes to the engineering strain, the formula is ln of L minus L0, and if you solve this, if we already know that Li minus L0 minus 1 is engineering strain plus 1, so you can add the same thing, engineering strain, which is equal to ln of engineering stress plus 1. This is how the engineering stress strain and the true stress strain are linked. Okay, so now we'll just deal with the results so that you can understand how exactly it's gonna vary. So does it matter, engineering stress and the true stress strain? Yes, it does matter. So as we mentioned before, there is no much difference between the engineering and true stress strain for the lower value strains. Okay, however, loading increases, the specimen begins to change its shape more drastically due to Poisson's ratio. This difference becomes relevant, and then we need to recommend to utilize the true stress strain data. So if you take the look at the table at the bottom, so when we're gonna cross the strain value more than 5%, you could see the difference. The stress where 18.2% when it comes to strain is 22%, so it keeps on increasing. If I consider the 200 engineering stress, the difference is 20%, 22 approximately, right? So true stress is 240 and the strain it is 0.18, right? And when it comes to initial two stages, you could see there is no much difference. 100 and true stress is 101, engineering stress is 150 and true stress is 157. The only minor difference is that when it comes to the more, it will completely change. So we recommend, if you're going to deal with the strain over 5% difference, you need to consider the true stress strain curves. I hope it's clear why we're going to use these things. Now we'll have a look at this failure theories. So for ductile, we have the Vollmeis's yield criterion theories, that is maximum distortion theory, we can say. Oxford yield criterion and Tresca criterion we consider for the ductile. Okay, most commonly Vollmeis's. When it comes to the brittle materials, Rankine theory and the Morse failure criterions, the Coulomb-Morse failure and the modified Morse failure criteria we follow. So if you want to know about these things more and more, I have the later on slides. So at the moment it will just go beyond my particular consideration. I'll keep it simple. For ductile, we use the one masses more maximum distortion theory. For brittle materials, Rankine failure and the Morse failure theories. It's clear. Okay. Now we'll have a look at the basic terminologies in FEA, that is Young's modulus, Poisson's ratio, and all. So when it comes to Young's modulus, what exactly it is? So this particular property is a measure of tensile stiffness of a solid material. So the stiffness, right? If you're going to consider the stiffness matrix, this Young's modulus is going to play a very important role. So basically it's slope, the straight elastic line stress strain curve in the figure. It is denoted by E. So in the form of Pascal, we're gonna just measure it. 1 Pascal, which is equal to 1 Newton per meter square. Okay, 1 megapascal, which is equal to 10 to the 6 Newton per meter square. Okay. So in the linear static analysis, if you're going to consider that into account, so the FEA will follow the Hooke's law. So it is under the elastic limit. The stiffness of the part follows the elastic portion stress strain curve. So majority of these, all the linear static analysis will follow the Hooke's law. We don't need to worry about it when it comes to nonlinear analysis. So we're gonna consider this stress strain curve along with the hardening rule. Okay. Now to find out this Young's modulus, the best formula is to utilize this example, that is yield stress 300 megapascal for steel or whatever you can consider. Strain is this value 0.0015. So to calculate Young's modulus, stress by strain according to the Hooke's law, so 15 into 2 is 30, so you can just add up this one and you will get this value. Young's modulus is equal to 200 gigapascal. Okay, this I can just deal with this Young's modulus. It's quite clear. When it comes to Poisson's ratio, so how does Poisson's ratio used in FEA? The formula is transverse strain to the axial strain. So it is the measure of the Poisson effect, we can say. So in simple, the deformation, expansion or contraction we can consider. Okay, so it will be used to measure the lateral contraction of a material when it is under the tensile stresses, okay, in the longitudinal direction. So most of the materials or the metals we can consider has the Poisson's ratio value from 0 to 0.5. Okay, like incompressible metal or the materials we can consider, like rubber, it is 0.5. It is completely incompressible. can see some of the values there. If you consider steel, it is 0.27 to 0.3, and if you consider copper, it is 0.33. If you consider the aluminum alloys, it is 0.32. If you consider rubber, it is 0.49, and it is 0.5. So particularly this Poisson's ratio will take into picture while dealing with the stiffness matrices of the plane stress, plane strain, and the solid elements as well as the plate elements. So in the figure you could see, right, the solid cube with the length L having the elastic material, okay, and the Poisson's ratio 0.5 subject to a tensile stress. When you pull it on either sides due to the pull force, the blue color cube will deform to form the pink color, right, where the reduction in the area will take place due to the force application. The cube expands. Delta L due to the tension and X direction contracted in YZ direction by delta L. I hope it's clear, right? The Poisson's ratio, why we use it, and what is the impact of the Poisson's ratio and FEA analysis. It is quite simple, so these things we need to know. So when it comes to basics, I would like to just explain in better manner. Okay, so if you consider the same bar example, so the formula becomes BL by A, where the B is the applied load, L is the length of the bar, area of the cross section A. Okay, most interesting thing is the Young's modulus, okay, which describes the property of the material. Okay, so with respect to properties of material, Young's modulus will be taken into account. So we can consider the same domain, finite element analysis. Once we discretizes, we'll be using the only finite elements here, only line element we can consider. Then our element stiffness matrix will make sure that Young's modulus is taken into account for the material. Okay, now the same thing, we're going to consider only the plane stress, the thickness, like we can consider the 2D elements here to deal with this. Tetrahedral or triangular elements we can consider to deal with this. So once we deal with this, we can have the results in the form of stress along x direction, stress along y direction, normal direction, and shear stress along xy plane. So if we consider these things, the formula will be, it will be taken into account like strain in x direction for stress along x and the Young's modulus plus Poisson's ratio into strain in y direction. Same thing for stress along y direction and the shear stress value, shear stress in xy plane, and rigidity modulus. Okay, so once you're going to consider these things, the shear stress can be represented using the Young's modulus as well as Poisson's ratio. So when you consider these things into account, the Poisson's ratio coming into picture. Okay, so which is very important while considering these forming the stiffness matrices for the plane stress, plane strain, and the solid elements as well as the plate elements. Okay, hope it's very clear. So why we consider this Poisson's ratio into account while dealing with the FE analysis. Okay, so this plane stress, plane strain, normal stress, normal strain, and the shear stress are going to come into picture to solve these things to form the stiffness matrix and all. This Poisson's ratio plays very important role. Okay, we'll see this aspect ratio, what exactly it is. Once you consider the aspect ratio to account, so it is the ratio of the largest dimension of the element to the smallest dimension. If I consider the triangle, the bottom length is largest one, right, to the perpendicular length. So this ratio should be equals to 1 or unity. So more it is distorted from 1, the lesser the result accuracy. Remember that. Okay, what are the truss elements? So these are the part of these truss structures linked together by joints. So we can consider the 1D elements, so which transmit only the axial force to the elements, not other forces. So the stiffness matrix, the formula is already you have seen, that is it's gonna take the number of nodes into account and the number of degrees of freedom, and it will solve the entire stiffness matrix to give the results in the form of strain or the displacement or the stress. Fine. So very important term is one more, that is residual stress. So what it is? So this exactly the stress which will remain in a component even in the absence of the external loading condition, thermal gradient we can say. Okay. In some cases, residual stress results in the significant plastic deformation, okay, leading to the warpage or the distortion in the body. So again, it might even affect for the fatigue as well as the fracture consideration. Example, in a weld component, okay, where you're gonna have this residual stress even after gap has been created due to this particular boarded joints. So there also you're gonna form this residual stresses. Okay, finally we'll see about this types of materials we're gonna consider, that is isotropic materials, orthotropic and anisotropic materials. So when it comes to isotropic, the material properties, the thermal properties as well, mechanical and thermal, are same in all the directions. Remember that, very important thing. So simply we can consider steel and other metals. Orthotropic, so this is completely independent of the directions, so mechanical as well as the thermal properties when it comes to the crystals, okay, and other rolled metals and all, we can have it. When it comes to anisotropic metals, the properties are dependent only on directions, okay, like we can consider the cloth, rubber and the wood and the composite materials as well. So these are only directionally dependent along one direction. Yep, so I hope it's clear. So these are the few things about the initial basic steps you need to remember. Yep, so that's all about this session. So in upcoming sessions I'm going to cover more and more detailed discussions on this FEA basics and the interview questions during uh, all these sessions. So I'd like your help to just improvise these contents. If you feel like I need to add some other contents, please do suggest me what exactly I can do. And I would also request the people who are watching, like who are already in the CAE domain and all, so if they want to help us to generate better content, if they want us to help to get more and more knowledge on CAE domain, please do contact us so that we can just produce the better content for users and young generation. Even this might help us to just have a better grip on CAE domain. I will look forward for your comments to just improvise our contents as well as to add a few extra things and all the basics needed for all the CAE engineers who wanted to switch towards CAE domain. Thank you guys. Stay tuned. Bye everyone.